NN training. So far, we've learned about recurrent neural networks, RNNs. RNNs are powerful tools capable of handling sequential data effectively. However, they struggle with retaining information over long sequences due to a challenge known as the gradient vanishing problem. But what exactly is gradient vanishing? To understand this, and the issue of forgetting in RNNs, we need to delve into how neural networks work. Learning in neural networks. Neural networks are graphs composed of layers, where each node, or neuron, in one layer, connects to every node in the next layer. Each connection, or edge, has an associated number, called a weight. In simple terms, the goal of a neural network is to determine the optimal weights for all connections so that the network can make accurate predictions for unseen data. For example, let's say we want the network to distinguish between pictures of cats and dogs. The network must adjust its weights in such a way that it can predict with high accuracy whether a new image is of a cat or a dog. To achieve this, we need a large dataset for training, which we provide to the network to learn the best weights. In this video, we'll explore how neural networks are trained. Training in neural network. 1. Initialization of weights. Initially, random weights, often 0.5, are assigned to all edges in the network. 2. Input layer. The input data is fed into the neurons of the first layer. 3. Forward propagation. For each neuron in the subsequent layer, the input is calculated as the weighted sum of all inputs from the previous layer. This expression shows that one neuron's input is the sum of all nodes in the previous layer multiplied by the related weight. A mathematical function, known as an activation function, is applied to this sum to produce the neuron's output. The process is repeated for each layer until the final layer, the output layer, is reached. F, in the above expression, is the activation function. 4. Output layer. The output of the network is compared with the target value, the actual label. For instance, if the target is 1, dog, but the network predicts 0, cat, it has made an error. 5. Error calculation. The difference between the predicted output and the target is called the residual. The smaller the residual, the more accurate the network. 6. Backpropagation. To correct its mistake, the network adjusts its weights using the residual. The residual is propagated backward through the network, and the weights are updated based on a method called gradient descent, a mathematical approach to minimize the error. 7. Iterative training. These steps, forward propagation and backpropagation, are repeated for all training data to optimize the network's weights and improve its accuracy. In RNNs, some connections and weights recur to capture sequential dependencies in the data, but the training process remains the same. Now that we've understood how neural networks are trained, let's revisit the gradient vanishing problem. This issue arises in networks with long sequences. During backpropagation, the gradients, residuals, calculated at the output layer decrease exponentially as they propagate toward the earlier layers. Over time, these gradients approach 0, making weight updates negligible. As a result, the weights stop changing and remain fixed. This phenomenon explains why RNNs struggle with learning dependencies over long sequences. The network effectively forgets the earlier parts of the sequence, which limits its ability to handle complex problems. Now that we understand the limitations of RNNs, the next step is to explore how long short-term memory, LSTM, networks solve the gradient vanishing problem. Stay tuned as we dive into LSTMs and their innovative approach.